about it right now.
Okay.
Emily, read that to us.
Me?
Yep.
A child slides down a slide at a constant speed of 1.5 meters per second. The height of the slide is 3 meters. Write down the equation for conservation of energy, noting the choice of system, the initial and final states, and what energy transformation has taken place.
Okay. So we may not be able to come up with final answers and things like that, but we can kind of get things set up and going here. So we've got a child at the top of some slide, and then they're going down the slide. I guess maybe I should make them sitting down and smiling. That just looks kind of scary. All right. We're not at the bottom of the slide just quite yet. So talk to me about the energy. Oh, yeah, perfect. Talk to me about the energy at the beginning.
Potential, pretty much.
Okay.
Most of it is going to be potential.
So
That's all it's going. Are we doing friction?
let's see. It's going down at a constant speed.
So
Are we doing friction here?
Well, if it's at a constant speed, I would think so.
Okay. Yeah. Why would if?
so it should be accelerated.
Otherwise, it'd be accelerating. Right. Okay. So if there's constant speed, that means that the force going down the ramp is counteracted by a force going up the ramp. So yeah, there's definitely going to be, here for consistency's sake, we'll also fill in the face there. So yeah, there's friction. So talk to me then about the energy in that.
Thermal and kinetic.
Okay. So there is kinetic and there is thermal. Write down the equation for conservation of energy. So the generic form is the energy initial plus any change in your energy is equal to your final. So the initial energy that we have is gravitational potential plus any change.
Which is the friction force for energy.
Okay. Well, is there any, I mean, when we talk about the change in the energy, we have to, you could talk about the change from kinetic or potential to kinetic and stuff like that, the change within the system, okay? Or you can talk about the change from without. And so this normally is referring to outside energy. So you've got the initial energy plus energy, or in the form of work or heat that is added to the system, okay, equals your final. So yes, if we want to, it's zero if, Gracie, we consider our system
The slide and the person.
the slide and the child. If that's the whole system, then there is absolutely no outside energy coming in. And then we have to talk about our final state. Since this is talking about the child as they're sliding down, right? Okay? Then let's make this right here our final state. Now, if that's the case, talk to me about the final state.
Yeah, kinetic and thermal.
You've got kinetic, you've got thermal energy, and since we're still sliding down, there's still potential energy.
Oh, that's
So they're not at zero.
Yeah. So I'll put UGF, and over here UG initial. So you can start seeing some of the things. Here our system is the child, slide, earth. That's the system that we're considering. Why does earth have to be in this system?
Gravity.
Yeah, for gravity. That's where we're getting that. We really don't, and then if we wanted to, we could say that potential energy, some of it is turning into kinetic and thermal. Okay? So this is just sort of like a conceptual discuss it type of a thing.
Do we have to break it down any further than that?
You could if you want to, MGH and stuff like that, but we don't know the height. They don't give us a whole lot more. 1/2 mv squared. I'd rather go to an actual problem where they do give us some numbers so we can calculate some stuff. which is Katie on the water slide. Alright, so there's the shape. The starting point is 9 meters above the ground. She pushes off with an initial speed of 2 meters per second. And if the slide is frictionless, which would be awesome, how fast will Katie be traveling at the bottom? So let's talk about energy. It's at before and energy after. Okay? And is there any work that's done on this system? Obviously, we're going to declare this as our initial situation and this is our final situation, so that's pretty much taken care of. This is the moment that she's now at the very bottom of the slide. Initially, talked about some of the energy that she has up at the top. Potential and kinetic. So put UGI plus KI. Is there any work or heat done on this system?
No.
Nope. If we consider the system as Katie and the slide and the Earth, there's nothing else reaching in and putting a force or moving or doing anything like that. So the change in energy is 0, and that's going to equal the final. What do we have going on here at the final? What sort of energy? Kinetic? That's it. Why no thermal? Because it's frictionless. Why no potential?
Because it's already at the bottom.
Yep. Now we have the choice to define that. We can say that this is the gravitational 0 line. That's we're going to make that decision in declaration. Yes.
What would be an example of change in energy?
If
What could happen, like?
okay, if in the process of doing this, someone was pushing her.
So like in a swing, like when someone pushes someone, then they will.
Okay, like someone, yeah, there you go. Like someone, like if she's on a swing going back and forth, left to herself, all of that potential energy. If I just pull my son up on the swing and I let him go, okay, and he swings back and forth, my sun, swing, tree, earth system, right? That's all one system. That potential energy is slowly going to turn. Oh, it turns immediately into kinetic energy, but then it turns back into potential. Okay, but not as much because some of it has turned into thermal up at the hinge, right? Okay. Also, some of it has caused the air molecules to kind of bump into each other and speed up a little bit. There's been a little bit of drag. Okay, and so some of that potential energy is also turned into thermal energy of the particles, these air particles. Eventually, if I let him go for about a minute or so, he'll come to a complete stop. Okay, we could do the same thing over here. All right, with this. Okay. Eventually, all of that initial potential energy is turned into kinetic and thermal. Okay? What Emily was saying is, if you continually add energy to the system, then the energy is going to increase. I'm doing work here. Okay? If I were to get a blowtorch, and heat it up, something, that would be another way of adding energy to that system.
I have a question. What did
Sure.
you say the kinetic initial that you said? Was that implying that there is kinetic energy?
Because we're told that she initially pushes off at 2 meters per second.
So we're starting from that instant, not she was just sitting there before she pushed off.
Right, because, yes. Alright, so since the formula here for potential, gravitational potential is mg delta y plus kinetic. Anybody remember what the...
1/2 times velocity squared.
And that's initial velocity. K final is going to be 1/2 the mass times velocity final squared. You'll notice that we get to avoid an embarrassing situation with Katie. We do not have to ask what her weight is, okay? Because we can divide this side by the mass and this whole side by the mass and they all cancel. Emily, question.
No, never mind.
Okay. We're looking for, what are they asking us to find?
For final swing.
Be final. Okay. So let's see, I'm going to multiply both sides by 2, so I've got, and then I'll take the square root. So V final is going to be the square root of 2 times G times delta Y plus, when I multiply the 2 times 1/2, it cancels. So then I just have V initial squared. So everything done at one time, it's 2 times 9.8, we'll just round up to 10. 2 times 10 times the delta y, what was her original height? 9 meters above ground
Yeah.
zero, so 9 plus initial velocity squared, so plus 4. So 20 times 9, 180 plus 4, 184 square root.
Why'd you put the 2 again? Over here?
I have 1/2 over on this side, so in order to get rid of that, I'm going to multiply it by 2 over here. And well, if I multiply this whole thing by 2, then the 2 gets here, and the 2 times the 1/2 is canceling that.
Okay.
I did 9.8, so I got 13.43 as my answer.
Okay, sure.
Yeah,
that's
that's
still
back.
Yeah,
approximate.
that's
I was
okay.
confused.
Okay, yeah.
13 point
4.
4, 3, so 4.
meters per second. Is that a reasonable speed
Mm-hmm.
for no friction? Well, maybe. Probably going a lot slower due to friction. Thermal effects. Glad we talked about that pendulum because that's one of the things we're going to be working on this week. We're moving on to chapter 14 after today, hopefully. Yep. That's all going good. That's what we got. 13. All right. So here, Kevin, your lucky day is another answer to your question. All right. So Kevin, read to us about Monica and her daughter here.
Monica pulls her daughter Jessie in a bike trailer. The trailer and Jessie together have a mass of 25 kilograms. Monica starts up a 100-meter long slope that's 4 meters high. On the slope, Monica's bike pulls on the trailer with a constant force of 8 newtons. They start out at the bottom of the slope with a speed of 5.3 meters per second. What is their speed at the top of the slope?
Okay. So, get some sort of slope. I'm just going to represent them with a box because I don't have time to mess with drawing a bike with a trailer. So the trailer and Jessie together have a mass of 25 kilograms. Monica starts up a 100-meter long slope. That means our delta x is 100 meters. That's 4 meters high. So that's how you would interpret that. Monica's bike pulls the trailer with a constant force of 8 newtons. So we've got a force equals 8 newtons all the way along that entire slope. Start out at the bottom with a velocity of 5, or speed, but we all know that's velocity, 5.3 meters per second. And they want us to find the final velocity. First question, what is the system?
Slope,
Bike,
bottom,
Trailer.
bike trailer.
So the ramp,
gravity.
Definitely-
object.
definitely the trailer, probably, someone say earth,
Yeah.
okay? But here's the thing, the bike, if we think about the bike that's pulling it, okay? We don't have any extra information on that. So think about this. If we
That's an
just
object.
consider the ramp trailer earth, then the bike which is pulling it along the way is an external force reaching in the system,
Yes.
which is going to be causing work to be done.
But didn't they give us a combined mass? So how could we separate them in those?
No, it's just the trailer.
The trailer and Jessie, which
And
is the girl
Jessie.
inside of it, yeah.
Oh.
Monica is that external force,
Okay.
yes.
This kind of seems like a dumb question, but like, how do you? I mean, what's to stop you from putting the bike into the system?
The fact that we could put that into the system, but you have to then think, okay, where is that number one, we're gonna need her mass, okay? And number two, what's the energy transformation going on if we consider Monica as well?
Okay.
And what is that energy transformation? If you consider the bike in there, right? And she's pulling it now, right? She's doing this force times the distance, right? Where is she coming up with that energy? Is it potential energy initially, or is it kinetic energy? It's where my athletes at. Where do you get the energy? Chemical from the food that she's eating. So we would have to do the if we're going to do the transfer, we have to say, okay, we got the chemical energy for the food is being transferred into the kinetic motion of her legs. Do you see where I'm going with that? Well, we might not have to, but that's part of the thing. But it's actually more convenient if we don't consider the bike. So we say energy initial plus the change in energy, that is energy that's been added into the system in the form of work or heat, is going to equal the final energy. Now, it's possible, I haven't thought through this one, we might be able to do this one with kinematics. Right? We've got an initial velocity. We want to know a final velocity. We know the distance. We could do a free body diagram. We have a force. Maybe we could draw a free body diagram, figure out what the acceleration was and all that stuff like that. Do you know what I mean? Mm-hmm. Yeah, but who wants to do that? This is just going to be a before and after picture. Okay? So, talk about the energy before.
Kinetic.
Yep, kinetic. Any potential?
No.
No. And 9 times out of 10 on these problems, you're not going to have thermal stuff. It's just going to be kinetic and potential. All right. So that's kinetic right there, initial. Plus the change in energy. Talk to me about the change in energy here.
Potential is going up. You have potential now.
Right. So that's over here in our final state. So we do have potential energy at the end, potential energy final.
That change in energy would be the constant force of 8 newtons, wouldn't it?
Almost.
But I don't know how to make it into energy.
Yes, right. That's the work equation.
The force times the distance.
Mm-hmm.
Okay.
The change in energy is equal to the force times the distance. Technically, it's the force times distance times the cosine of the angle, but since the displacement is in the same direction as the force, that's a cosine of 0, which is going to give you a value of 1. It's you can go straight to the pre-AP version, just force times distance. Okay?
Well, that's why we needed to know the 100 meters.
Yep. Force times distance. So initial K, so we've got 1/2 mv squared plus force times distance equals, oh, I guess I forgot about this one over here. Kinetic final. So we have mg delta y plus 1/2 mv final squared. It might be actually on this one easier if we just plug in some numbers. I don't know, maybe. Do we have mass in every term?
No,
we don't
not
have
in this.
Are we not considering friction going to thermal?
Good question. Are we going to consider?
I mean, the bike's not.
Oh, I have it on my notes here. Ignore friction.
Oh, okay.
Yeah, because that naturally some of that energy would be turned into thermal effects. Yeah. Or we could say that's a net speed. Okay. So we've got 1/2 times the 25 times the initial velocity, 5.3, plus a force of 8 newtons times the distance, 100 meters, equals the mass, 25, times gravity. I'll use your 9.8 times 4 plus 1/2 times the mass, 25, times the final velocity squared. So you take that times that squared plus that plus the 800 minus all of this divided by 1/4, take the square root.
Sorry.
Give me an approximate value.
I got 3.7.
That's what I got as well.
Okay, great.
But this isn't a math intercalculating class, so I'm just going to kind of leave that for you as an activity. Okay, so before we move on to the new things, talk to me, class. Talk about systems. What are some of the things that we have to do with these type of problems?
Analyze them.
Okay, gotta analyze them. Keep going.
Break down the equations.
Okay, absolutely. Once you have those terms, it's just a matter of plugging in 1/2 mv squared or mg delta y. What else?
You need to choose what items are in your system.
Yeah. Normally you're not going to have anything that's really too complicated, okay? We're going to just kind of keep it pretty straightforward. I would write this down almost every time. Initial energy plus the change is equal to the final. You know, that's if you have any change in, you know, any external forces, okay? Any work done on the system. If there's not work done on the system, then you're left with just your straightforward final equals initial, or initial equals final. That's one of the great things. Okay? All right. 10.7, which I am going to check all your notes here at some point. Let's look at that very quickly. Oh, there's a girl pulling a bike trailer. $13.7? Nope.
They left it square. That's what it was before you square root.
Oh, take the square root. Okay, that'll be 3.7, which is about 8 miles an hour. All right. So we're going to revisit collisions now. Probably read about this. So when you've got those two objects and they're sticking together, then that is a perfectly inelastic, because you think of elastic, you think of it like bouncy, all right? So an inelastic is a sticky situation. If you have inelastic, one of them completely bounces away from the other, everything's good. You get into some problems with energy when you have the sticky situation, when one of them kind of sticks together, okay? Because think about what happens that has to happen at the molecular level for two things to kind of stick together.
You have to bond.
You have to kind of deform, yeah, maybe bond. It's gonna, and in the process of moving those molecules and stuff like that, it's going to alter how fast those molecules are moving, okay? And we call that thermal energy, right? So when you have two things that stick together, then you're going to have some of that initial kinetic energy turns into thermal, okay? That's going to be a big thing. So with these sticky situations, they really are kind of sticky because the kinetic doesn't get transferred all to kinetic after the collision. It's all kinetic beforehand, some kinetic, some thermal. Turns out it's a lot thermal, okay? We're going to find out just how much. Let me give you this next set of notes. All right, so this is actually the same problem we did back in chapter 9, where you've got two trains that are colliding, and these two train cars actually. This one has a mass of 2 times 10 to the 4th, so that 10 to the 4th is like 10,000, so 20,000 kilograms, 40,000 kilograms, okay? Now, they're not moving very fast, only 1.5 meters per second. They collide, and then afterwards, they're joined, they're connected, okay? And they're traveling in this direction at 0.25 meters per second. So this one's going at 1.5, this one at negative 1.1. So you notice they're combined, they're going slower than either one individually, which is what we would expect. It's just sort of like, look at that. This one's going a little faster, you know, and they kind of do this. There we got the visual, okay? Now, we've got everything. Kinetic initial, and kinetic final, okay? What we want to do is, we want to figure out, does all of this energy before match all of this energy afterwards? Okay, so here we go. So the energy initial is 1/2 mv squared plus 1/2 mv squared. All right, so let's type that in real quick. Help me out here. 1/2 times the mass 1 times velocity 1 squared plus 1/2 mass 2 times velocity 2 squared. Do you know what you do? Kevin, just add those two numbers up. Somebody give me a calculation there.
4, 6, 7, 0, 0.
4, 6.
Is it smaller than that?
I don't know. It seems pretty large. I don't actually.
I got 4,600 also.
4,600.
46,000.
Are we supposed to use the negative for the velocity? But that doesn't
Well,
matter either.
it doesn't matter because you square it.
Yeah,
So-
I got 46,700.
46,700. Anybody else agree or disagree?
I got them.
Okay. Units on energy.
Joules.
Joules. All right. Now, these two things are combined. Let's figure out what the final energy is. Okay. So it's still going to be 1/2, but the masses are going to be added. Let's see if we can make our life easier. This is 10 to the 4th is 10,000. All right. 10 to the 3rd is 1,000. So this is 20,000. This is 40,000. So add those two together.
60,000.
60,000. So 1/2 60,000 times velocity squared. It doesn't matter about the negative; this goes away. So 0.25 squared.
I got 1875.
So
So
what was the change?
1,875 joules. What? You're right.
Oh. Okay. Yeah.
You're about worried.
Wait a sec. I mean, what in the world?
There was a change.
There was definitely a change in that kinetic energy, in that total energy, right? Well, actually, I can take that back. Not the total energy, the kinetic energy. All right. So can't lie with this, Kevin. Do you see how much? What happened to the other 45,000 joules? All went to thermal.
That's pretty cool.
Yeah. In fact, let's figure out just out of fun what the percentage is. What's the difference between those two?
44,825.
44,825. Take that as a fraction of 46,700. So do the 44,825 divided by 46.
96%.
96% of the energy is lost due to thermal effects of that collision. Pretty crazy, huh? All right. There are some new formulas that you need to be aware of. I'm going to skip a little bit about this. In the textbook, they give you conservation of momentum, conservation of energy. Just as a side note, I guess sort of like wrapping this thing up, if you're going to do a problem of a collision, okay, you need to think about, is it sticking together or is it not sticking together? If it's sticking together, do not use conservation of energy. Okay? Is there conservation of energy?
Yeah.
Yes. But will your formula work for you?
No.
Probably not. Why not? Some of it's thermal. Unless they tell you how much energy goes to thermal, don't use conservation energy. Instead, use conservation momentum. And if you're like, what was momentum again? That was just the mass times the velocity. It's the result of Newton's third law.
Wait.
And yes,
Sorry, so if it's elastic,
that
so
means totally
it bounces
bouncy.
off,
Yep.
then you can use energy conservation.
Mhm.
So there's no thermal energy involved in that?
If it's 100% elastic, there's none.
Oh,
But if it doesn't say that, then you have to. Are you assuming that on all of them? If it
They'll
doesn't say it-
they'll let you know. 100% elastic or or not. Okay, so that's just something. Your book goes and gives you some specialized formulas dealing with when the masses are the same. I'm not really interested in that. I'm more interested in thinking about how. By the way, I normally have a public safety announcement at this point. Wear a helmet because it transfers some of that energy into the foam getting crushed rather than your skull getting crushed. Okay, so there you go. That's a public service announcement. We're going to go to power. We have to talk about power. This is a better situation, sort of, to kind of think it through. Look at those first three situations, okay? Someone is 80 kilograms going up 10 meters, 80 kilograms also going up 10 meters, but in less time, okay? Someone going who weighs 64 kilograms going up the stairs, but in that 8 seconds, okay? So I want you to think about what's different in each one of these situations, all right? If you've got two people going up the stairs and they're twins, right? Yeah, it's the speed, okay? So up until now, time has not been an issue. If we've just been talked about the work done, it doesn't matter, whether or not they do, this one and that one, okay? They both have initial energy and final energy, all right? And it doesn't matter, we talk about the path, but think about the time frame. If this one goes up really slowly, and this one, it gets there faster. Obviously, there's something that's different about those, but it's not the energy. The energy is the same. What's different is the amount of energy over that time period. And so that's sort of a new concept, a new quantity, and that's what we call power. So if you don't have it in your notes on 10.8, go ahead and write it down. Power is the change in energy over change in time. In fact, that's also one of the remaining formulas on your formula chart. Okay? So you can think of it, power, it's how quickly the energy is transferred. High power means there's a lot of energy going in a short period of time. Low power means maybe not so much energy and maybe it's over a longer period of time. Okay? An alternate form of this is apply your work energy formula. The change in energy is equal to, so the delta E is work. Or alternate form, work, as we all know, is equal to force times distance. We'll do the pre-AP version. So force times D. But then we're going to switch back into AP mode. Instead of writing distance, we're going to write delta X. And now your kinematics training is kicking in. Delta X over delta T, velocity. So the power that is done is on an object is equal to the force on that object times the velocity of that object. Okay? So if we're transferring power, the amount of power that I'm transferring to this ball is going to equal the product of the force and the velocity. And that makes sense. If I put more force into it, then our understanding of power is more power being delivered. It's higher velocity, same thing. So the units for power is joules over seconds,
Also known as watts.
which is known as a watt. A watt. Yes. A joule per second. You have 1 joule of energy transferred over 1 second, then that is 1 watt. Okay? So 10 watts would mean 10 joules per second. 746 watts, so 746 joules per second,
1 horsepower.
is 1 horsepower. Okay? So, let's think about this particular situation here. Which one has the largest power output? Which student is outputting the most power?
I feel like we're being
Well, B and C don't have the displacement.
None of them. Well, we'll assume that it's 10 meters. Assume that
Well,
it's 10.
D is.
The take is 20. It goes has a vertical change of 20, but it's over the course of 25 seconds.
Oh,
You
right.
know what I'm saying?
Yeah.
So we could naturally assume, if they're going at a constant rate, that this person would travel the 10 meters over the course of,
Oh, 12.5.
assuming that they're okay.
Thank you, that helps.
All right.
Their force, their weight.
Yes, you could think of it as their, well, I wouldn't even think of, you could do it the force times the velocity, but I would not think of it like that. I would think of it as the change in energy, okay? The student at the bottom of the stair has 0 potential energy. Up at the top, they have potential energy mg delta y.
But we're thinking about it like the same height, then they're pretty much gonna have the same.
They will,
Except
well,
the 64 kilograms.
I know, yeah. So let's just go ahead and let's figure out out of A, B, and D, who's got the most power.
Can't be A or D.
Can't be A, D because this person's going faster.
Yeah, but
Right.
it's the same.
Okay. So really, we're looking at this one: mass times gravity times delta y versus this person's mass times gravity times delta y.
And it would have to be B because a higher mass.
Right. This one has a higher mass, and so therefore, it's going to have more power. So this is power is delta E over delta T. So you're looking for the largest E and the smallest delta T. This one has the smallest delta T, and it has the largest mass. Okay. If you turn the page over, I have this problem, but it's not essential that we do it. It really just is showing mass and the speed and the time, and it's literally just multiplying the numbers together to find out, if you have, if this is your velocity, so I'm not really concerned about that one. This one, we might do this problem later on. We'll see if we have time tomorrow. Otherwise, we'll just, you've got this actually, I think this example's in your book. So you might want to look in the textbook for that too. All right, that's going to finish it up for chapter 10. We wrapped it up with power, working our way backwards. We talked about elastic and inelastic collisions. Okay, conservation of energy and thinking about the system. And what is energy, and the different forms of energy: thermal, kinetic, gravitational potential, elastic potential. If you want to look on the Google Classroom, that we're doing something a little bit different this week. We're spending 2 days on a lab, and then a quiz on Thursday, and then Friday, your groups will present to all of us about what you found out in your lab. So I'm super excited about that. All right, see you next time.